So firstly, good morning, everybody, or good afternoon, actually. It's just gone afternoon. So, guys. So, if you could not talk, that'd be fantastic, because it makes my life. Excuse me, lady in the blue jacket. Lady in the blue jacket. Excuse me. Thank you. So it makes my life super difficult if you're talking. So if you talk, I will stop the lecture and interrupt you. Now, part of the reason why I do this is it's just my personality. It's that if I hear a conversation going on, like that one over there, I will try and focus in on that conversation and hear it, and that just distracts me totally. So it's just, I find it much easier to concentrate and give a good lecture if it's quiet. So I'll just wait for these guys to come and sit down. There's some mini handouts there, guys. Yeah, just take a couple. Right, so this lecture's called Analog Electronics. So we've now left digital electronics. In about 6 lectures' time, I'm going to come back to digital electronics, and I'm going to do a little bit of mathematics with digital electronics. Those of you in the examples class, who is in the examples class? Hands up. Okay, so you guys will have done a little bit of Boolean algebra already. I'm going to come back to this in one of the final lectures. So if you missed the examples class, it's okay. We'll cover some more of that again, but we'll go deeper into it. So having said that, we've basically now left digital electronics. And that's it. So you've had your 3 lectures of digital electronics. So this is how quickly this course is moving. So it's that important. So now we're on to analog electronics. And I've called this lecture, Every Idiot Can Count to One. And that's a famous quote by a man called Bob Wilder, who we'll look at later. And what that means is basically digital electronics is easy, analog is hard. Okay, so he spent his life designing digital circuits, analog circuits, sorry. So last lecture we managed to cover race times, and I didn't manage to do that the year before. So what I'll do is I'll recap race times very, very quickly, and you treat that as a recap of last lecture. I'm then going to move on to analog electronics, so totally new topic. We're going to look at something called operational amplifiers. And I'm going to talk about what an op-amp is, or it's called an op-amp for short, or operational amplifier. Then we're going to look at 2 fundamental op-amp circuits that you guys should know about. And they're basically so useful that, you know, in your project you could very easily... Oh, is that chips? No, that's not chips. It's pasta. I'd like some chips. So there's two fundamental circuits that are very, very useful for you guys to know about. You know, that every engineer should know about them. So let's look at race times very quickly. So who was here on the last lecture when we covered this? Who was here? Who wasn't here? Right, so there's a few hands. I'll cover this quickly. So race times, the thing about race time, or all the digital circuits we've covered till now, basically assume that the signal propagates through them instantaneously. Okay, and race times start to be a problem when you think they're real chips and signals don't propagate through the chips instantaneously. And they're called race times because you can think of it as sort of electrons racing each other through the circuit, or, you know, horses racing each other along different routes. So we looked at this circuit where we had basically an AND gate, and we had a 1 going into a NOT gate, which is going into... So we've got a 1 going into a NOT gate. What will the output be? 0. We've got a 1 going into an OR gate. What will the output be? 1, right? We've got a 0 going into a NOT gate, so we've got a 1 here, or the entrance to an OR gate. What will the output be? 1, right? So we've got 2 circuits that both produce 1 on the output. And I said, well, what happens in the ideal world is if you flip the circuit, so if you go from a 1-1 condition to a 0-0 condition, in the ideal world, the output of the circuit will stay high because that's what the logic says it'll do. But I said in the non-ideal world, so this is the ideal world, we go from a 1 and a 1 to a 0 and a 0, and the output of the circuit stays high. But I said in the non-ideal world, obviously all gates take time to react. They take, you know, because there's capacitors in them, there's transistors that we'll come and learn about later, and these are real physical components that take a time to react. So that this NOT gate will take a certain amount of time to react, and this time here can be between nanoseconds and microseconds. And what happens as a result is it takes a while for this NOT gate to turn on, and therefore the output of our circuit is low for a little bit. So actually this circuit's giving the wrong answer for a little bit of time simply because of this delay that the NOT gate's introducing. And I said this is, you know, I'm telling you about this. I'm not going to go into massive detail. I'm telling you about this because your digital circuits, when you design them, may not work. And this is one reason why they may not work. And it's fine if it's, you know, I don't know, for a light or something in your house, this circuit. But this could be attached to a warhead or something. You don't want the output to the detonator being wrong, even for a small amount of time, because it could be bad. Okay? Whoops. I think my pointer's gone crazy again. Right, so that's it. So that's a recap of last lecture on race times. Anybody got any questions on race times? Happy to answer any questions on race times. No? Any other questions from last lectures? Nope. Okay. Right, so now we've left digital electronics. We're now moving on to analog circuits. So you can get an introduction to this if you want to read along with this book. I guess you've all got this Introduction to Mechanical Engineering Part 1. These are the page references. There's some very, very good electronic engineering books that I'll recommend probably next lecture if I get a bit of time on this subject. And this subject, analog electronics, is really, really huge. And I think, how many pages is that? 6 pages. 6 pages definitely does not do it any justice. So your electronic engineering friends will have tomes that thick on this subject. So if you want to read around, feel free. So until now, I've only taught you about digital electronics and digital processing information. And in a digital signal, we have basically a 1 or a 0, a 1, a 0, a 1. That's all there is. It's binary. There's no 0.5s. You know, it's either 1 or it's 0. Okay. However, the real world is not binary, as you may have figured out. So here's an example of a real-world problem that you might see. You might want to record some speech, and my speech that I'm speaking out is not a binary signal. It's an analog signal. The amplitude of my voice goes up and down, and it looks a bit like this. So I think this is some song that I think this is a song we looked at in the in MATLAB lectures, and you can see sort of the amplitude of the signal the signal looks very, very different to this. So this is a binary signal, and this is an analog signal, and it'll take values between 0 and 1. And, you know, really, it can take any value between 0 and 1, and you can get this off guitar, and very, very, very often, you know, any real-world signal you record will be an analog signal. It's very rare it's a binary signal. You know, a door being opened and closed is binary, but if you think about, I don't know, accelerometers for your car, the sensors in that camera, they're all going to be analog sensors because they're sort of always measuring the magnitude of a real event. So, yeah, so why are you teaching me about analog electronics? Because everybody says, oh, I don't want an analog TV or an analog whatever because it's old. Well, you know, isn't everything digital nowadays? Don't we have digital TV, digital radio, digital satellite? Well, yes, we do have, everything is digital in the world these days, but all electronics is digital in the world these days, but the real world remains analog, and therefore, if you want to interact with the real world, you always need like an analog input stage to your digital circuits before you can start doing your digital computation. So here's an example. So here's an example of a real-world digital voice recorder. So if you go, I don't know, so I went to MISCA and I bought some MP3 recorders, and it said digital MP3 recorder, you know, fantastic quality, sound quality. But always in these digital devices, there's going to be some analog electronics on the input stage. So what will happen is you'll play your guitar or whatever, your microphone will have a diaphragm in it that produces sort of a voltage depending on how far depressed the diaphragm is. And then this sort of analog signal, very, very small analog signal, so maybe 0.1 millivolts, and really, really small analog signal, will have to be amplified by your analog electronics. So very often the signal that comes off sensors is just too small to do any processing with. So you need to boost that signal a bit before you send it to your digital electronics to something that's a bit bigger. I'm not quite sure what's comes next. Yeah, so there's a list here of various things that you can use analog electronics for. So you can use it to clean up signals. So if you've got a very noisy signal, before you send it to your digital encoder, you can clean up the signal very nicely with your analog electronics. You can use amplifiers. So amplify, you know, even your brand new, spanking new hi-fi amplifiers, you know, they're definitely going to be analog. So effectively, anything when you're processing real-world signals will have some analog electronics to boost the signal, clean it up, or whatever. So here's some examples. Audio-visual preamplifiers. So, anything where there's audio-visual data. Clean-up signals. Voltage regulators are very, very important. So they're very, very important analog components in all digital equipment. So when you get, when for example, on this thing, it's got a couple of batteries in it, and it's got some digital transmitter in it. The power the digital transmitter will want to have may be like 3.2 volts, and the power or the voltage the batteries supply will be maybe 5 volts or something. So there'll be some analog piece of equipment in here that is regulating the power the batteries supply to the digital circuits to make sure those digital circuits always have the right voltage. And as the batteries, as the voltage in the battery goes down over time through the lecture, these analog circuits will adjust the supply voltage to digital circuits. And then amplifying small signals from sensors. So analog electronics is all around us, and whenever you want to interact with the real world, you're going to have an analog circuit. It's not all digital. Right, have I convinced you about the importance of analog circuits? Vaguely? Yeah? Good. Right, so here's an overview of today's lecture again. What we're going to look at is what is an op-amp and what are they used for. So this is an actual op-amp chip. If you buy, you can buy these, and there's all different types and classes of op-amps. And you can see there's my biro, and this is on my computer. Very often op-amps come in 8-pin little packages, and they're ever so tiny. And in there will be 1 or 2 op-amps. And if you buy, I don't know, if these are in some if your op-amp's in a video processing chip, you might have many of these integrated onto one chip. But as far as you're concerned, if you're integrated projects and things like that, if you want an op-amp, they're going to look like this. Yeah, basically. And you'll find them in loads of pieces of kit. Now, I think that engineering is often taught as a very dry subject, and you just talk about facts and stuff like that. And they might tell you about somebody called Newton who had long hair and did something a long time ago. But all this stuff you're learning about now was done in sort of the 70s and 60s by really interesting people, sort of people that almost of our age, of our time period. And some of them are very, very interesting characters and sort of, had very interesting lives. So I always think it's good to tell you about the people behind these wonderful ideas and inventions before we actually go into them. So this gentleman here is called Bob Wilder, and he was basically a genius. And I know genius is misused a lot, but he was just very, very clever and eccentric engineer. And what you're looking at there, so that's him, and what he's got his hands on there whilst he's smoking his cigar, this is sort of the blueprint for what's inside this chip. So he basically designed these chips, and they did it. I don't think there were any serious computers in those days, and it was all done on sort of big sort of microfiche films like that. And all the chips, in principle, we're going to look at now, it were sort of his babies in effect. Okay, they may have been updated and whatever, but he was the first guy to really do it. And he was a famous man that said every idiot can count to 1. Meaning, like my job that I do, which is analog electronics, is very difficult, and all these digital people, they're wasting. They're not. That's easy. That's what he said anyway. And he was. So I'll read this quote. Okay. So Wilder lived the life of an alcoholic loner who went on all night long bar binges. He liked to fight others when drunk, but regularly overestimated his own abilities in such confrontations. On one occasion, he was absolutely clocked by the offender Mike Scott, a future CEO of Apple Inc. However, the story about Wilder bringing a goat to trim the lawn in front of his office was incorrect. It was a sheep, and he brought it in his Mercedes-Benz convertible for just one day. He later abandoned her in the nearest bar. So this is some of the work of this guy we're looking at. So he lived a very interesting life, sort of at the forefront of technology in 1960, 1970. And he's worth reading about if you've got a chance. So what's the purpose of an operational amplifier? Why am I telling about this? Well, the word is basically, the phrase is basically summed up in the 2 words. So it's operational and amplifier, okay? When you think of operation, you think of mathematical operation, so, like adding or subtracting, that's an operation you do on stuff. And amplifier means making a signal bigger. So what this is a chip that amplifies, so makes stuff bigger and does mathematics. So that's what we're thinking about. Okay. So here we go. But what's inside this op-amp? So what we're going to do is open up the top of this op-amp and have a little look at it. Now then, I don't want you to be scared. Don't get scared. This is what's inside it. Yeah? So actually, by the end of this course, you could probably have an idea of how it works. Now, I would never put this in an exam, say, draw that out or something like that, because that would be really, really mean. But basically, the point I'm making is that when you have a chip like this, so it's called an integrated circuit, because somebody's integrated onto it. I don't know. I think there's like at least 30 transistors on there or something. Somebody's integrated all these transistors onto that single chip. Oh, with these resistors and capacitors. What's missing? What component don't we have on there? We've got resistors, capacitors. What don't we have? What don't we have? What's missing? What's Arthur been telling you about all this time? It's not on there. Have a look. Ah? Inductors. Yeah, inductors are actually very difficult to put into chips. So very often you try and fake it with capacitors and resistors. Anyway, the point I'm making is very often in electronics is that we don't need to understand the whole circuit to be able to use a component. Because, if you had to think about that circuit every time you want to go and use this chip, you'd go absolutely mad. So what we do as engineers is we say, well, that's far too difficult for me to understand. What I'm going to do is draw an equivalent circuit or a model, and I can use this model to understand the circuit. So we're going to simplify all of that into this. Okay, much better, right? I heard a sigh of relief. So if we look at this circuit again, we've got a non-inverting input. I've even lost the other input. Inverting input and an output. So we've sort of maintained that, this, and this. Boom. So inverting input, non-inverting input, and the output. So the nomenclature is always the same. So always inverting input, non-inverting input, and output. Okay. So in this model of our circuit, we've got two resistors. We've got resistor R in and resistor R out. Now, R in is the input resistance. So this is the resistance of the stuff this is the resistance of the signals we put into the circuit. And generally speaking, in an ideal op-amp, R in is very, very big. It's basically infinite. So we can assume the input resistance is infinite. And then we've got an output resistor, and this is called R0. And do you notice this? This is actually a voltage source. So we're sort of this little battery in the op-amp. And this is the output resistance. And usually, in an ideal op-amp, R out is very, very small. In fact, it's so small, we can consider it 0. So we've assumed this is, or I'm telling you, the assumptions are, this is infinite, and this is 0, okay? So we can simplify this simplified model much further. So do you notice we get rid of, because this is infinite, we can get rid of it, boom, and it becomes an open circuit. And here, because this is effectively 0, we can get rid of it, and we have a short circuit. So this is our simplified model. And this is much easier to analyze, or circuits like this are much easier to analyze than ones with these resistors in. Any questions so far? Any burning questions? Okay. Do shout out, please. If you've got any... yeah? Sorry? Say again? No, it won't. No. So a resistor with infinite resistance, there's no current flowing through it. So, yeah, okay. So, now then, let's continue building this equivalent circuit of an operational amplifier. So, I'm telling you now that the output voltage, V out, is proportional to V in times A, okay? So A is known as the gain of an amplifier, okay? So gain is how much bigger the signal of your amplifier makes it. So you can think of it, if you buy a, I don't know, if you buy a stereo amplifier, it's going to amplify the signal from your CD player by a factor of, I don't know, 100 maybe, if it's a really good one. So A will be 100. So it's like, how much louder does it make the signal? And also notice on this diagram, see this arrow is pointing upwards. This arrow is pointing downwards, because that means I'm sort of measuring the voltage the other way around. You could rewrite this expression with this arrow pointing upwards, but you have to put a minus in this equation. So I've just flipped that arrow to make the analysis much easier for us. So, yeah. Well, I think my batteries in my pointer are going low. There we go. Right, so this is the idea of an op-amp. It's pretty simple. Here we've got the input. So we've got a little input signal, so a tiny little sine wave. So you can think of this as, you know, maybe the tiny little electrical signal my voice is making by speaking to this microphone. Think of this tiny little signal that's going down this wire. So that's this tiny little signal here. And out of this op-amp comes this massive signal on the other side. And you can think of that as the current that's being delivered to the speakers in this auditorium. So we've got V out here is equal to V in times A. But what's A for a typical op-amp, okay? So this is not a simple answer. So, you know, I could say, oh, A is 10. It's not. It's a little bit more complicated than that. So this is the gain curve of a typical operational amplifier. So you can see, so this is frequency at the bottom. So 10 to the 1, 10 to 2, 10 to 3, 10 to 4, 10 to 5, 10 to 6, 10 to 7. So 10 to the 6 is like a megahertz, okay? So these aren't just used for speech. These can also be used for sort of, you know, radio frequency signals. So 10 to the 6 is a megahertz, so that's sort of, you know, that sort of transmission sounds. Whereas, I don't know, 1 to the 10, that's very, very deep voice. And, you know, maybe, I don't know what range the human voice is, up to about 44 kilohertz. So the human voice is probably here. So, you know, we use these devices around here at the moment with my microphone. So this is sort of the frequency range that might work over. And this is the gain up the left-hand side. So 10, 100,000, 10,000, and it goes up and up and up to a million. So what you can, and notice this is a log scale. So this is log, and this is log. So what you can notice is that over the gain of these operational amplifiers changes dramatically depending what frequency you put into it. So if you put, you know, 10 hertz into it, you'll get loads of gain. You'll get a factor of about 1 million. Okay? And if you put in a megahertz into it, you'll get no gain. You'll get like 2. So if you can imagine using one of these to amplify a telephone signal, I mean, if you had a deep voice, if you're a man and you had a deep voice, your voice would be amplified a lot like that. It'd be really loud, right? But if you had a really high-pitched female voice, the voice wouldn't be amplified at all because it's sort of higher pitched. And it would be awful. And also different parts of your speech would be amplified different amounts because they contain different frequency components. So this is a nightmare for engineers because you can imagine a telephone system where deep male voices were amplified a lot and female voices were hardly amplified at all. It would be just awful. So this is a problem. This nonlinear gain curve is a real problem for engineers because not all amplification happens at the same level. So that's a big problem. So this is the other problem with them. So imagine we had a signal at 10 hertz. So I want you to think about it. 10 hertz. So here we've got a signal coming at 10 hertz. So this might be, it could be an earthquake, or it could be, you know, the sounds from an earthquake, or it could be really deep components of my voice. And the gain at 10 hertz is 10 to the 5, okay? So what would V out be at, so how much would my voice be amplified if it had a 10 hertz component in it? How much? So we've got an input signal of 0.1 volts. What would the output voltage be? 0.01 times, so 0.01 times 10 to the 5, what voltage have we got in the output? What do you think? Guess. You multiply, 1,000. Yeah. Now, 1,000 volts out of this amplifier. Now let's just go back and look at it. Do you think you're going to get 1,000 volts out of that? No. Imagine plugging that thing into the mains, it would go bang, and that's only 240 volts. So we're not going to get 1,000 volts out of that. So what this means is, what this is telling me is that, so you got it right. So this seems quite high, and also especially if this component is only running off 5 volts. Okay, so these things are running off 5 volts, but our man's calculation there says it's going to give us 1,000 volts. This seems strange. Well, it's not going to give us 1,000 volts. What actually happens is something called saturation. Okay? So here's the ideal case. We put in 0.01 volts, and I said 10,000. It's actually 1,000. And we get out of our op-amp 1,000 volts. And this clearly is not going to happen. But in the real world, we're running our op-amp off a 5-volt supply. Okay? So what actually happens is this. You put in your 0.01 volt signal, and then the op-amp tries to give you 1,000 volts, but it can't. So what it does is it goes up to its maximum supply voltage, 5 volts, and then it goes, oh, I can't give you any more. It then goes flat, and then once your signal goes down, it goes, okay. Then it tries to give you a minus 1,000 volts, but it can't. So it'll just give you, like minus 5, and it says that's all you're having. So can you see it? Can you see the output's basically being chopped? Okay, so you're not going to get your 1,000 volts out of it. So we've got two problems with our op-amp. We've got our nonlinear gain, which is, voices being amplified at different amounts depending on what frequency components they have, and we've got output clipping. So this isn't good, okay? And it's all basically down to this nonlinear frequency response. So we've somehow got to get rid of, if we want to use our op-amps, this nonlinear frequency response, okay? So this is what we do. So the next topic, we're going to do 2 circuits, and basically they're not very difficult. I'm going to go through them slowly, but I suggest after this lecture you have a little go with a pen, try and scribble out, try and do the derivations yourself. So the inverting amplifier. So to solve this problem of this, so we'll go back. To solve this problem of this massive gain and that it's nonlinear, what we do is the following. We take a proportion of the output voltage and we stuff it back in the inverting terminal of the op-amp. So it's like a negative feedback. We're taking some of the output and we're stuffing it back in the beginning to try and sort of dampen down the output. And it's sort of a negative feedback loop. And this is called the inverting, so this circuit here is called the inverting amplifier. And it's a very, very famous operational amplifier circuit. And in effectively any piece of kit you buy, anything, there'll be one of these inverting amplifier circuits. And it's sort of the go-to amplifier, in effect. So it works by basically taking some of the output and stuffing it back in the beginning. And can you see we've got 2 resistors in series here? What does this remind you of? 2 resistors in series. What does that remind you of? Arthur's been teaching about these. If they're between a supply voltage and 0, what would you call it? Something beginning with P and the second word D? Potential divider. Yeah, so potential divider. So what this is doing is basically sort of sending some current back and dividing effectively the voltage. So you can think of it a bit like that. I think my battery is flat. And the result of doing this is actually quite dramatic. What we do is we take, this is called our open loop gain. So this gain here is called our open loop gain. And once we stuff in this resistor and this resistor to funnel back some of the input to reduce the gain of the amplifier, the gain drops from this crazy, like a factor of 1,000,000 amplification to like 10. And you can imagine, like, if my voice here was being amplified by 1,000,000 times, you'd probably hear me in Beeston, right? But it's being amplified now by a factor of about 10, which is quite comfortable to listen to. So this turns this circuit into this component into actually a useful circuit that that you can use in your electronic devices. So we now got a useful gain, and also notice it's flat from about 0 hertz all the way up to about 1,000,000 hertz. So this is also a sort of uniform profile. So now we no longer have our female voices being amplified less than our male voices in our telephone system. So what we're going to do, now I think, is it that bad? No? Wrong lecture. Now, I think this is the hardest bit. He's left at the wrong time. Because I think this is the hardest bit of all these lectures I'm going to teach you. So this lecture and my next lecture, I'm going to do derivations of op-amps. They're a bit mathematical, but it's worth knowing about, because when you go to industry and somebody says, can you do me an op-amp circuit for this, it's quite handy to at least have this in your notes, even if you can't regurgitate it on the spot. So we're going to try and do the analysis for this circuit now. So just bear with me and try and concentrate, and it'll be pretty easy. So how much gain? So if I give you a random operational amplifier circuit like this with an input resistor here and an output resistor, or a feedback resistor like this. And I say, well, it's going to amplify the input, and it's going to turn it into a bigger output signal, okay? But the question is, how much bigger is this output signal to our input signal? So what I'm going to teach you now is a general method for analysing operational amplifier circuits, okay? So you can apply this to any circuit, and very often, as we'll see later, you can smack in capacitors and inductors or whatever you want to make very fancy circuits. But this method will work with all operational amplifier circuits, and it will tell you how big the gain is. So in general, what we need to do is we need to write an expression linking the input voltage here to the output voltage here. So that's the gain. That's what we're trying to do. We're saying, how much gain do we get? Okay? We want to link the input to the output here. So this is my sort of system of doing it. What you do firstly is write an expression relating the input voltages, so input voltages, to the output, to the voltage of the terminals of the op-amp. So we want to relate this voltage here to the voltages here. Then we go write an expression relating the output of the op-amp, so this bit here, to the input terminals of the op-amp. So we somehow want to relate this voltage to this point here. So we're basically doing sort of voltage analysis on two loops. Then once we've got an expression relating this voltage to this voltage and this voltage to this voltage, we can sort of combine them using, using algebra, and then we get an expression sort of linking the two parts of the circuit. So I'll run over it again. Relate this voltage to this voltage, relate this voltage to this voltage, then there's sort of these two expressions should have common elements, and then do a bit of algebra, and we get the expression relating the input to the output. Any questions so far? No? Just jump on me. If there's any questions, just jump on me, and I'll very happily answer. So the first thing to do when analysing electronic circuits, so all this will be on Moodle, so you don't need to scribble it down like mad, unless you really, really want to. I'll put it all on Moodle. The general trick to analysing electronic circuits is label all currents, label all voltages, just write them down, because they might be useful later. So that's the trick that I'm going to teach you with this. So basically, here's our input voltage. We're going to have a current I1 going in there, fair enough. We're going to have a current I going into there, have a current IF going into there. So we're just labelling it. I'm just labeling. This is nothing clever, just like labelling it. You can call it A, B, C, D, E if you want, but I'm just calling it like this. We know we've got a voltage here, and we know the voltage here will be equal to A times V, because that's an equation for an op-amp that I've just told you. Yeah, so I think we've put some numbers on our resistors. Yeah, so we've done a good job of labeling it. Now the first thing I always say is let's just write down the easy equations to do with operational amplifiers, or when you're analysing any circuit. So we know the resistance in our op-amp is infinite. So if you want infinite resistance, how much current can flow? 0, right? No current flows through an infinite resistor. So we've said the input to our op-amp's infinite resistance, so no current can flow into it. So I is 0. Okay, so that's solved one thing for us. Now we can analyse this current node here. So Arthur's been teaching about analysis of current in circuits. And, well, we know I is 0, and we know electrons can't be destroyed or created by going through a wire, right? So we know that I1, here's I1, must be equal to I or minus IF. Now, I've noticed I've defined the arrows going this way and the arrows going this way, and that's why I've got a minus here. So you could define the arrow going the other way, and you could get rid of the minus. It'll all work out fine, but I've just done it like this because it's a bit easier. Okay? So I think I need to go over that. So now, let's link the input voltages to the voltages at the op-amp here. So let me just look how much time I've got. I'm sorry. How long have we got? 10 minutes. Ages. 13 minutes. We do loads of stuff in that time. So here's the input voltage. Here's the voltage going into our operational amplifier. So this is the first step in the process. Link this voltage to the voltages here. So we can just apply sort of voltage law, so Kirchoff's voltage law, and we can go input voltage here must be equal to the voltage loss over this resistor, which is I1 times R1 there, minus V, which is the voltage here. And then this is a 0 volt drop because it's just a wire. So we sort of analyse the voltages in this loop here. So we've gone this voltage must be equal to this current times this voltage minus this. So that's one equation, okay? Now, let's look at the end of okay. So what we've got here is we've got two unknowns. We've got V in, we've got I1, and we've got V. Now, what we can do is, because we know V out, so V out here is equal to A times V, we can substitute this into this expression, and we get Vn equals I1 times R1 minus V out over A. Okay, so we've now sort of got rid of that unknown V from one of our equations. Okay. So now we can apply Kirchoff's voltage law to. So we sort of described from here to here. We can now apply Kirchoff's voltage law to relate this voltage here to this voltage here. So let's look at this. V out here, so that's what we want, must be equal to I times RF, so that's that one there. And then between here and back down to here, it's V, so it's minus V. And again, we know, so we've got this equation here, we've got V in of the operation amplifier is equal to V out, or V out equals A times V. So we can substitute that into this equation, and we get equation 3. So we've now got three equations. We've got one we derived by looking at this part of the circuit, one we derived by looking at this part of the circuit, and we've also know the current going around this current node. And if you notice, this equation was defined in terms of IF, and this equation was defined in terms of I1, but we know I1 equals minus IF. So we can substitute them all together, and we get the answer. So this is the answer. This is the equation describing this circuit. Now, in an exam, so when I mention the word in an exam, you've always got to listen really carefully to what comes next, like really, really exactly. In an exam, it would be very, very mean of me to ask you to derive this circuit. What I might ask you, though, in an exam is to ask you to derive a little bit of it. So I might say, how do I relate V here to V out? The answer's V out equals A times V in. Or I might ask you what the impedance of or what's the input resistance of an op-amp, at which point you'd say infinity. I might ask you, what's the resistance of an output of an op-amp, at which point you'd say 0. So, or I might ask you, little bits of this, but I'm not going to say, or it'd be very mean of me to say anyway, please derive this, blah, 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 because that'd be a bit mean. So anyway, we've got this equation relating V in, V out, and we've got all the resistors, and we've got the gain of the op-amp. Now, A is very big. Yes. So this here, so V out over V in is the gain. So therefore, this expression here is the gain. And can you see there's a minus here? Can you see there's a little minus? What that tells us is it's an inverting op-amp. It means that the input signal is going to be flipped because the gain is negative. So when you put in a positive voltage, it will go negative. And that's why this is called the inverting op-amp. And this expression will basically give us this curve here. Okay? And if we say A is much bigger than 1, so A is massive, if we say A is 1,000,000, we can simplify this expression to gain equals minus RF over R1. So we just now simplified it in terms of two resistors, and we can calculate basically practically the gain of an op-amp circuit. So here's an example exam question. An inverting amplifier circuit has an input resistance of 10K and a feedback resistance of 1 megaohm. Using the open circuit gain versus frequency plot for the 741 op-amp, calculate the exact closed loop gain at 10 hertz. Okay? So what you do is you get this equation, which you probably have to remember. I probably wouldn't give this to you. You pop in these two numbers, and you get minus 100A over A plus 101. Because you just pop these in there. And then we'd say at A equals 1 times 10 to the 5. So 10 hertz gains 10 to the 5, pop that in there, and the gain would be a factor of 100, about. So that would be sort of what I'd expect you to do in the exam. So you might need to know the equation, be able to read off the graph, the gain, the frequency, and get a reasonable answer. Okay? So it's now going to be your go. High-speed trains must stop when there's an earthquake. All the trains will derail. You're designing an earthquake detection system for a new generation of high-speed trains. You're listening for earthquakes with a microphone attached to the side of the tracks. Earthquakes produce a lot of vibrations at 1,000 hertz. During an earthquake, your microphone will produce 0.1 volt sine wave. Your microphone will produce a 0.1 volt sine wave at 1,000 hertz. You have to design an operational amplifier circuit with R equals 1,000 and RF equals 1,000, R1 equals 10 ohms. What will the output voltage be of this amplifier when the quake hits? So, go. That's not quite the answer. Yeah, so we've got 1,000 hertz is what you've got to remember. That's where you're reading this graph off. So calculate the gain. Okay, go. So you haven't got much time. You've got like 60 seconds. So we're looking for a value of V out. And what's V in? V in, yeah, you've got all the numbers there. Have a go. It shouldn't take you more than a few minutes. So literally, just pop the numbers in the formula. You right here? What do you put in for A? You read it off the graph. So the question is, what do you put in for A? You read A off the graph. So you don't have long. Anybody got an answer? Anybody got an answer? Who's the first to get the answer? Anybody got an answer? So basically, pop those numbers in and read the value of A off the graph. Have we got an answer? Got an answer? What'd you get?
Minus 99.89.
That sounds reasonable. Minus 99.89. I got minus 9. Factor of 10 wrong somewhere. Could be me, could be you, don't know. Anyway, you've all had a go at that. You've all had a go at that. So this is a typical thing. Sorry, can I just have your attention? Guys? So this is a typical thing you might have to do in an exam. So I just want to go through practical op-amps. So we've got 5 minutes left, so this is definitely not the end of the lecture, don't start packing up. When you buy an op-amp, guys, I can't talk over you. Right, so when you go and buy an op-amp, in fact, when you go and buy any chip at all, it'll come with a data sheet that looks like this. So if you Google op-amp whatever data sheet, you'll get something like this. And what it'll do is it'll give you the various pinouts and or it'll tell you how to connect this thing up, basically. And your op-amp can come in different packages. So this is the round package. This is a package like this one here. And if you zoom in on this diagram here, it looks like this. So this is basically the op-amp. And can you notice there's a little hole in the chip there, a little tab. That basically tells you which way round the chip's going to be. And you've got inverting input, non-inverting input, output, a bit of power. I think that's power. That's the earth. So that's how to hook it up. So you can actually go and buy one of these now and hook it up. NC means not connected. VCC means positive, and VEE means earth. So now I want to show you. So in these data sheets, you'll find very useful things like supply voltage. So this one can be run off plus or minus 18 volts. And very often in these data sheets, when you see a value like you can run it off minus 18 volts or plus 18 volts, that's how to break the chip. So it will run off 18 volts, but I wouldn't run it off 18 volts. I'd run it off 16 or 17. So these are very often the maximum limits. And it'll often say recommended and maximum, so don't go to the maximum. Now what can we see here? In these data sheets there's often lots of traps. So what can we see here? Operating temperature, 0 to plus 70 degrees C. So where wouldn't you want to use this? Where wouldn't you want to use this? In the Arctic, well, in your car even, in winter, right? So you wouldn't put this in your car because it would stop working at 0 or it would give you wrong answers. So read these data sheets very carefully and you'll have less accidents. And in these data sheets, you're also, so I made this curve up, but this is a typical curve you can find in these data sheets. And it'll give you this and then you can do your calculations and it'll tell you how to use the op amp. So this is a very, very, these data sheets are practical. In an exam, I may even give you a data sheet and say, tell me something. Now, summing amplifier. The question is, do we have time to do this? I suspect not. No. So it's 10:02. I'm not going to gallop through this because it deserves a little bit more attention than me galloping through it. So what I may do is I may go through this in either on Friday or I'll go in the examples class, or I may go through it in the next lecture. Okay? If there's any questions, just ask them now. I'm very happy to answer questions. Thank you very much.